So let's look at this particular example. Now the first one I have shown you is an example where the load is concentrated and a deep beam like this. The load is concentrated and it's acting. So you can see in this situation, this angle can be easily calculated because the way that the loads are transferred is from here, it will be transferred over to this particular location. Whereas let's consider a case of a deep beam where it supports a uniformly distributed load. So a deep beam is supported by two columns, 400 by 250 millimeter cross section. The length of the beam is 5.2 meters and the height is 3 meters. Height is 3 meters, and it is loaded by a UDL of 350 kilonewtons per meter. Perform the structural design with strut and tie method. We can use the 25 megapascal concrete. So 25 megapascal means 25 megapascal of cylinder strength. So the equivalent cube strength is 30 megapascal. So this is the cube strength, this is the cylinder strength. So C2530 concrete means cylinder strength is 25 newtons per millimeter squared, or the cube strength is 30 newtons per millimeter squared. So let's see what happens here. And if you look at this diagram, you can see that you can clearly see that the loads are transferred along lines like this. But in these areas, you can see the loads are transferred in a reasonably vertical direction as well. So what actually happens is, in a deep beam, generally you'll find that if you look at the lever arm is about 0.7 times the effective depth. So what you find is, initially the loads will be transferred vertically, and halfway through they will start being transferred over to the supports as inclined forces. And you can actually look at our earlier model and see whether we can modify it to suit this condition. And so we have a height of 0.5 meters here. So I'll save it under a different name. Save as D4. So 1, 2, 3. So I can delete all that. And also I need to have, so these are the exact example, but we'll use something similar to see how the stresses will be transferred. So the example, we are applying a load of something like UDL of 350 kilonewtons per meter. In this example, the length of the beam is 5.2 meters, height is 3 meters. UDL is 350 kilonewtons per meter, and the supports are 400 by 250. But in this one, supports will be 500, length will be 6 meters, height will be 3 meters, and we can apply the same load. So we select. These are the exact model, but I'm going to show you something similar. So I'll undo it, and I'll make the height 3.5 meters here, because for 5.2 meters we are using a 3-meter height. So I'll make the height slightly more. And let's just apply 350 into 0.5, 175 sine join loads, sine join load, live, something like. So you can see the loads that I applied, 175, and we can ask it to analyze it. So if you look at this diagram, you can see the loads are transferred along this line, and in these areas the loads are transferred almost vertically, but in this area it can be transferred onto these lines. So basically you can clearly see the loads are transferred here, this way and this way, and some of the loads can be transferred this way as well. So that's a kind of diagram that we are looking at. So basically, if you look at this situation, these are the maximum stresses. You'll see that, you know, the loads are transferred this way, and in these areas the loads will be transferred in a reasonably vertical direction, and after that it will be transferred into inclined direction. And here you can see that, you know, you get tension, and here also you can see, here you can see clearly you get tension, and here you can see these the plus forces, and these are the minus forces. These are in compression, these are in tension. So you can see clearly, see, you can see this region is in tension, this region is also in tension, but to a lesser degree, whereas this region is in compression. And if you look at the values also, you can see the minimum is at is minus 367 at an angle of 35.87 degrees, and here the minimum is minus 486 at an angle of 28.129, and then in these areas you will find that the part of the load will be actually compression in a vertical direction, close to vertical direction. So what actually happens is the loads will be transferred here, and after that it will be transferred this way, and the tension will occur here. So this gives an indication of how this the load transfer will take place. So if you look at this one, here you can see clearly, see in this area the load transfer will be almost vertical but slightly inclined, and these areas clearly you can see the inclination. So we say the load transfer that takes place will be given by a strut and tie model of this nature, and we say the UDL that acts here will act as a concentrated load, which will transfer the load to this level, and we consider this level about 0.7 times the 0.6 to 0.7 times the effective depth. And because this is a deep beam, you'll find the effective depth and the total height also may be almost same. So you'll see that because this height is 3000, I have selected this particular location at a height of about 2000 millimeters, giving a ratio of close to 0.67, close to 0.67 on the basis of the full height. So you see that, instead of UDL, we are going to consider that, it will be a concentrated load. So the load from here to mid length will be transferred here. From mid length to end will be transferred here. And initially the load transfer will be almost vertical in these areas. And after that it will become inclined. And in this area, because this is in compression, this is in compression, this also will be in compression. This region also will be in compression. And if you think this as a beam, then we know this will bend like this. This will go into tension, and this region will go into compression. So in the Strut and Tie model also, we are considering something similar. Strut and Tie model also, we are considering something similar. And we are getting some compression here. The vertical loads transferred to this level. And then the loads are transferred to the support as inclined forces in a strut. And the forces in the strut are all balanced by the tie. So do you have any questions on this model, equivalent model? So once you run a FEM with plate elements, we can get an idea about the load transfer. So once we get an idea about the load transfer, we have to actually work out an equivalent model so that we can maintain reasonably close angles for these struts. Otherwise, we have no guidance to see what is the angle of the strut. But once you run a FEM model, you can clearly see what's the type of angle that you have to use for the strut. So any question on this? So we are going to say the beam that is subjected to a UDL having a height of 3 meters, length of 5.2 meters, supported on 400 by 400 millimeter long supports, can be considered as equivalent to this particular Strut and Tie model. Any questions on this? Anything you would like to ask? Any questions, please? Anjali, do you have any questions? Or Chamini?
No, sir.
No?
No, sir.
Okay. Right. So we'll now see how this model can be checked. So the first thing is to find the values of C1, and so C1 will be equal to QL divided by 2. And before that, we'll see, how to find this angle theta. And here you can see this is 4,800. So half of that is 2,400. So on this side you get 1,200. On this side also you get 1,200. And this 4,800 is from center to center of this support. So in this area and this area, the load will be transferred here. And this length is 1,200. The side is 2,000. So you can actually work out this angle. and the guidance for the angle comes from this particular FEM model. So when you look at it, for a deep beam, the lever arm is generally about 0.6 to 0.7 times the depth. So I have considered that this as 2000 millimeters, which is a reasonable value. So the tan theta is equal to 2000 divided by 1200 or 1.67, or angle is 59 degrees. So the angle is 59 degrees. Then we have to see what is the value of this force or force in this particular element, which is equal to C1, and C1 is equal to QL divided by 2, QL divided by 2, and Q is 350. The total length of the wall is 5.2 meters divided by 2. You can see the load transferred here is 910 kilonewtons, and that load will be now resisted by the load vertical component of the force in this strut. So we can say C3 sine 59 is equal to C1. C3 sine 51 is equal to C1. So you can see C3 sine theta is equal to C1, or C3 sine 59 is equal to C1. So C3 is equal to C1 divided by sine 59, or 1061 kilonewtons. So always you have to keep in mind, we are resisting the vertical load by using the force in the strut. So the force in the strut should be higher than the vertical load that we are resisting. So the vertical load of some magnitude is resisted by the force in an inclined strut. So the force in the inclined strut should be higher than the vertical force that we are resisting. So you will get 1061 kilonewtons as the force C3. And the moment you know the force C3, we can find the horizontal component of that. So that is C3 cos 59, and that will be equal to the tensile force T1. So it will be C3 cos theta is equal to C2, or C2 is equal to C1 cos 59 divided by sine 51. Because if you substitute from this equation, C3 is equal to C1 over sine theta, or you can say C1 divided by tan 59. All these gives the same result. So you can see finally C2 value is 546, and that is also equal to C2, also the same situation, and C2 is the compression, and that is actually resisted, that is due to the horizontal component of it, horizontal component of C3. So that is equal to C3 over tan 59, C1 over tan 59, or C3 cos 59, C3 cos 59, C1 over tan 59, or C3 cos 59. So all these give the same answer, 546 kilonewtons. So the tensile force that we have to resist is 546 kilonewtons. So you can see how much reinforcement to be provided. The reinforcement to be provided is equal to force divided by the strength. Strength is 0.87 times 500. So you can see 1255 millimeters squared of cross section is needed, which can be provided by using two numbers of 20 millimeter bar, that is 314 into 2, 628, plus four numbers of 16 millimeter bars, that gives some 804, 804 plus 628, 620, 8 plus 804 gives 1432 square millimeters, which means that would be adequate to resist this tensile force. So we can find the reinforcement here, and generally this reinforcement will not be concentrated at the bottom of the member. We generally distribute it over 0.1 to 0.15 of this depth, 0.1 to 0.15 of this depth. So depth is 3000. So over about 300 millimeters, 350 millimeters, you can provide 300 to 350 millimeters, you can provide this reinforcement, because we need two numbers of 20 millimeter bars, which can be the bottommost, and then you can have two more bars of 16 millimeter concentrated within the first 300 millimeters of the DP. So this way you can make sure the tensile stresses are adequately looked after. And if you look at the FEM model also, you can see this area you get a lot of tension, and here also you get some tension. So what you generally do is, we concentrate it somewhere here, the reinforcement, and these areas you will be providing some nominal reinforcement, which will prevent any cracking, in the wall. So this is the situation. Now we have to see whether there can be crushing in these struts, and for that you can you can identify two different situations. Now here you can see some compression. So in this area you get CCC condition, compression, whereas here you get compression from the supporting column and compression from this strut C3 and tension. So this is CCT type joint. So we have to find what is the strength of struts. We have to find what is the strength of struts. So in compression nodes where no ties are anchored, K1 is 1. So sigma RD max is K1 nu FCD, where K1 is 1 and nu is this one. And we are using 25 megapascal concrete. So you will find that this 15 for 25 megapascal concrete. At a CCC node, you get a strength of 50. So whereas at the bottom node, where you get compression and tension, you get 0.85 times this value, and that gives 12.75 megapascal. So we know the strength. Now we have to find the stress. We know the strength. Now we have to find the stress. And how we find the stress is by looking at the width of the strut. We know this wall is 250 millimeters of thickness. So we know the width, the breadth of the strut. Now here we want to find the width of the strut. And the width of the strut will actually depend on, how we are going to support it and what is the width of the support. And width of the support is a 400 millimeter column. And here you can see we are providing some reinforcement. And this reinforcement can be concentrated over a height of 360 millimeters, and this is an arbitrary value that I have selected. But generally, you can see it complies with the rule that, when you are providing the bottom reinforcement can be within 0.1 to 1.5 of depth. the bottom reinforcement can be distributed over 0.1 to 0.15 of depth of the beam. So 0.1 is 300 millimeters. So I have selected 360 millimeters to distribute the reinforcement. So this reinforcement consists of two numbers of 20 millimeter bars and four numbers of 16 millimeter bars. And they are provided over a height of 360 millimeters. Because here you have to see that, we get the cover to the reinforcement as well. And in addition to that, whatever the reinforcement that comes in the vertical direction, we generally bend it and make it anchored here. So because of all these reasons, you will see that the height of 360 millimeters may be reasonable, which means now we can see what is the width of the strut, and width of the strut will be 400 millimeters. This angle is 59, so the 90. So this angle will be 31. So you get 400. If you draw a triangle here this way, so this angle is 31. So here you get an angle of 31, and we want this length, this particular length. So that will be 400 cos 31. And then you can also find the contribution from this side of 360, that will be 360 cos 59. So altogether you get 528 millimeter width for the strut. And we have to make sure that the concrete in the strut will not fail. We have to make sure that the concrete in the strut will not fail. So what we do is, we can check the stress in the strut. And the stress in the strut is force in the strut divided by the area. And the force in the strut is C3. You can see force in the strut is C3. So the force in the strut C3, you have to multiply it by 10 to the power 3 divided by the width of the wall, and this dimension 528, which gives the width of the strut. So that gives us stress of 8.03, and that is less than 12.75. that is allowed. That is less than 12.75. that is allowed. So basically you can see that this particular arrangement will not have any problem. So we can just provide the nominal reinforcement that is recommended for a deep beam or a wall, depending on whether you are designing a deep beam or a wall. So this is a common situation that can arise in shear walls, where the shear wall is supported by two piles and a ground beam. So generally you can have two piles and a ground beam and support the deep beam directly on the piles. So you can have something like a deep beam, something like a capping beam representing the pile cap, and then on top of that you can support the wall. So what actually happens is the loads in the wall will be transferred to the supports with deep beam action, where the loads will be transferred to the support as inclined loads, creating a strut in the beam. And you have to make sure this strut will not fail in crushing of concrete. So that's why you have to perform a calculation like this. So any question on this? So instead of this this particular column that we considered here, you can easily get two piles. So any questions? So next one is the same example where we are going to have wide supports. So for this, I will just create this FEM model so that, you know, after the break, we can look at the problem. So what I do is very quickly, I will create the FEM model. I'll make use of a new model. So here you can see that we'll create a new model with grid only, and the x direction we need 0.4 meters, y direction we need let's say 0.4, z direction 0.5, and this direction we need grid spacing will be number of grid lines will be 5.2 meters. 5.2 divided by 0.4, 13. So we need 14 grid lines. And the height of is 3 meters. So you need 7 grid lines. 2 grid lines. Height is 3 meters. So you need 7 grid lines. Grid spacing is 0.4 x direction, 0.5 y direction. And get this. Number of grid lines in x direction 13. Number of 2, 7. X direction 0.4. Y direction 0.6. Z direction 0.5. And then we'll define section properties, area, wall 250, and so it's okay. And then view, and then define load patterns, live, okay, and then you can draw 5.2 going up to height of 3 meters. Right, so you can see now we have the model, and so in this problem we are looking at the column size is 1000 millimeter by 250. Length of the beam is 5.2 meters. Height is 3 meters. There's a UDL of 600 kilonewtons per meter acting. So I have to get this as these 400, 800. I have to get a support of 1000. So what I can do is I can actually highlight these two and edit areas 2:1. Okay. So now I can actually assign the supports, and I will assign a joint restraint, but other locations I will only 1, 2, 4. Now it's 1, 2, 3, 4,000. Here also you get 1,000. So then we can assign joint restraints. That. And then I can also assign loads here. And the load is 600. 600 multiplied by 0.2 is 120. So these will actually have a load of 120. Assign joint load of live minus 120. And here I will get 60. Assign joint load of minus 60. And here I will get assign live load of minus 60 plus, that is 60 plus 120, 180. And then these places I'll get 240. So those are the loads. Now we can analyze it and see what happens. Let's say D5. So if you display, here you can see the way that the loads are transferred. And one of the things you can see is that, here, if I show the display, now here you can see this area is directly supported by the column. And here we are having a white column, which can actually represent the situation we can get with a pile cap supported by a pile. So let's say we have decided to go with 2 piles at these 2 ends. So in such a situation, you will get a pile cap, let's say 1 meter long. And so basically what happens is there's a pile underneath. So these are rigid zone, fairly rigid zone if you consider this area. So the chances are that, these loads will all be supported directly. Because if you look at the deformed shape also, you can see that argument. And if you look at the deformed shape under live, you can see here the deformation is very small, 0.4 millimeters, whereas here the deformation is about 0.7 millimeters. These 0.4 millimeters, these about 0.7 millimeters. So this area is deforming more. So chances are that, whatever the forces that come here will be transferred directly. So in that such a situation, using the deep beam action, what you have to transfer? What you have to transfer will be only the forces acting in this area. Will be only the forces that will be acting in this particular area. So these forces can be transferred directly downwards because this is a fairly rigid area of the deep beam. So no need for these forces to go this way and then come back. These forces will actually act directly. So that is also one of the theories, because when the load transfer has to take place in compression, it will take the shortest path. It will take the shortest path. So all these loads will be transferred directly downwards, whereas only the loads in these areas will be transferred through the strut, So is that clear? Any questions on this? So you can see, say, a very similar wall, but the loads are different. Support conditions are different. So you might treat it in slightly differently, because one is having a small support where the rigid zone over the support may not be significant, whereas the other one is having a wide support where the rigid zone over the support can be a significant portion, where we can consider the loads that would be transferred directly. So we don't have to worry about those forces being transferred through a strut. Those can be transferred directly. So if you look at this situation, you get some loads transferred vertically downwards directly, some other forces transferred this way. So there will be certain concentration of stressors in this area, and sometimes whatever the reinforcement that comes from the column, you might continue over to a certain distance, so that the areas where the high stress concentration is there will be enough reinforcement to carry the vertical loads. The reason is this area we get the vertical loads transferred directly, and also this area inclined, and those are all combined here. Is that clear? Any questions?